right, now we're going to take a look at section 5.9b. And so here we're looking at normal force and multiple body systems, that kind of thing. So let's get started. Body's in contact with the surface surface pushes on the body with a force that is normal to the surface, right? Normal means perpendicular. And so in A, there's no applied force. The only thing that the surface is fighting against is gravity. And so that would be 50 newtons pushing up. That's the normal force. In B, you've got 10 newtons pushing down. And so that means that the normal force has to fight gravity and that 10 newton force. So the normal force in B would be 60 newtons. In C, there's a 10 newton force up. So that's relieving some of the force of gravity. And so the force of the surface is just going to be 40 newtons. What's up? Sorry for the interruption. Okay, and then D, for part D, there's a 10 newton force, but it's at an angle. And so there's only 5 newtons down, right? If you do 10 sine of 60, sine of 60 is 1/2, and so it's 5 newtons down. And so that's what the normal force is fighting. Gravity plus the 5 newton force from that applied force. And so the normal force is going to be 55 newtons. In an elevator with the monkey, if there's no acceleration, then the normal force is just the weight of the monkey. If the elevator is accelerating upward, then the normal force has to be more than the force of gravity. You know it this way. If this is the monkey, not the elevator, but the monkey, here's mg. If it's accelerating upward, that means that this force has to be more than this force. So the normal force is more than this. Again, that just means acceleration upward. That doesn't mean it's moving upward. It might be slowing down as it's coming down. And then if it's downward acceleration, that means that the downward force has to be more than the normal force if it's accelerating downward. If we were consistent, like this is the exact same problem and the exact same setup, but just a different acceleration, then these 2 arrows should be the same length. But in this situation, our monkey gained some weight. So I'll do that. Anyway, no friction on the ramp. This is a different type of situation where we have normal force. And let's do a little bit of geometry so we can see where this angle ends up. We're going to be doing this quite a bit later on, so let's just start it now. On the inclined plane, this is the angle theta, and so here's the block, whatever it is, that's there. So I want to know, this is going to be Fg equal, this normal force will be equal to Fg times something, right, sine or cosine of the angle. Well, if I draw a line here that is parallel to the bottom, then these are alternate interior angles. So this is also theta, right? And then I can draw a line downward. And so if this is theta, this angle here is 90 minus theta. Right? But then I can also draw this. So this, excuse me, this now is perpendicular to the ramp. So if this is perpendicular to the ramp, then these two add up to 90 degrees. So this is theta. Right? And so this is the one that is opposite. So that's the angle. So here's theta. This then is Fg cosine of theta. And this parallel force pulling down is Fg sine theta. But we're looking at the normal force right now. So it would be that. If I add a force that's parallel to the surface, something here, Fa, this doesn't affect the normal force at all because it's perpendicular to the surface, or rather parallel to the surface and perpendicular to the normal force. And so Fn is still Fg cosine of theta. But now if I have some force pushing in this way, right, some Fa, then I can break this up into components parallel and perpendicular to the surface. And this is theta, same as this. So this one is Fa cosine theta, and this is Fa sine theta. That means the normal force has got to be Fg cosine theta plus Fa sine theta. Because Fa sine theta is this component. It's the component that's pushing into the surface. So the surface has to work against that. Again, Newton's third law, when we're looking at these things, two bodies interact, the forces of the bodies on each other are equal in an opposite direction. So if I have two bodies that are pushing against each other, whatever the force is on mass 1, so here's 1 and here's 2, let's say that they're attracted to each other, because it doesn't specifically say here. If this is the force of 2 on 1, then this is the force of 1 on 2. They're equal in magnitude, just opposite in direction. And you know, if we look at whole systems, if we make the system big enough, then everything is there. All the objects are included, all the forces, they're all internal, so how does anything ever move? There's a question that I've seen. Imagine that you're hooking up a horse to a cart, you're getting ready to go, and the horse turns around and says to you, you know, according to Newton's third law, no matter how hard I pull on the cart will pull back on me with equal and opposite force. So it's impossible for us to go anywhere, so you may as well just unhook me from this cart, and we shouldn't really do any work. How would you answer the horse if he said that to you? You know, first of all, you check your sanity, make sure you're feeling well, and then you're talking to a horse. But the idea is that what we're looking at is the net force on the object. So if the system is the horse and the cart together, then you're looking at all the external forces on that system. And if you're looking at just the cart, then you look at the forces on the cart. Why does this work? It works because we pay attention to systems. What are the objects in the system? And we look at the external forces. We draw free body diagrams, and it all makes sense. So if this is the cart, let me make a little space here. If this is the cart, what are all the forces on the cart? We've got the force of gravity, we have the normal force. These two should be the same. And then if this is the force of the horse on the cart, as long as this is more than this, the force of friction, or any other forces that might be there, then the cart will accelerate forward. If we want to see, the thing is, Newton's third law pairs of forces are always drawn on separate free body diagrams. They never go on the same object because they're always exerting forces on the other objects. All right, so here's an example.
Attention sophomores.
They're doing an announcement.
Your Six Flags forms are today in Steam Hallway.
Okay, that was informative. And the next thing, we have these 3 blocks like this. Here's M3, here's M2, and M1. This is 3 kilograms, 5 kilograms, and 2 kilograms. And there is a 30 Newton applied force on this frictionless system. Okay, so we want to know, find the applied force and all forces between the blocks. Oh, sorry, we don't know this yet. I just wrote that in. If the frictionless system accelerates at positive 3 meters per second. So there's acceleration here of 3 meters per second squared. Okay, so how do I find what the applied force is? Well, again, sigma F equals ma. So what is the total mass that's accelerating here? Because this force is accelerating that whole thing. So F is this total mass, which is 10 kilograms, times 30 meters per second squared. And so the force is 30 newtons. Really simple. Now I want to know, what's the force that 3 exerts on 5? Right? M1 exerts on M2. Well, if that's the case, so let's write it this way. The force of 1 on 2, let me write it that way. Force of 1 on 2 is equal to whatever this total mass is, and this total mass is 7 kilograms, times the acceleration, which is 3 meters per second squared. Sorry, this should be 3. I jumped ahead of myself there. 3. And so this is 21 newtons. Okay, that's the force of 1 on 2. What about the force of 2 on 3? Well, this force is accelerating just this one mass, which is 2 kilograms. And then the acceleration is 3 meters per second squared. And so that comes out to 6 newtons. Okay. Now there's a trick here, and the trick comes in this way. If I want to know the force, say between these two, what I do is I take the total force, this total force, and I multiply it by the ratio of the mass that's being accelerated to the total mass. So the mass that's being accelerated here is just 7 kilograms. And the total mass is 10 kilograms. Right? What does this come out to? 30 divided by 10 is 3 times 7 is 21 newtons. Right? And then notice that's what we got down here as well. This trick works because everything has the same acceleration. Same thing for this, when we're doing this. I can analyze all these as one single body because they all have the same acceleration. Same thing in example 2. Let's take a look at this. All right. In the first situation, the system is moving upward at 3 meters per second, and that means it has 0 acceleration. That means the net force is 0. Right? So the net force is 0. What are all the forces? Well, there's the force of gravity, negative force of gravity, plus the tension equals 0. So we're looking at this tension, and what I'm going to do is this. I'm going to say this is T1, T2, T3. All right, so we're looking at T1. So let's look at T1 first. So T1 is equal to Fg, and T1 is holding up all of these masses, right? So T1 is equal to m1 plus m2 plus m3 times the acceleration due to gravity, times 9.8 meters per second squared. So that's T1. T2 then, it'll work the same way. It's just T2 is holding up these two masses. So T2 is m1 plus m2 plus m3, or sorry, not m3, m2 times 9.8 meters per second squared. And then T3, of course, is only holding up that last mass. Sorry, this should be masses 2 and 3. And this one is only holding up m3 times 9.8 meters per second squared. Okay, that's part A. Part B, though, in part B, it's accelerating upward at 3 meters per second squared. So now, this is not 0. I'll erase this for now. This is no longer just 0. Sigma F equals m total times 3 meters per second squared. And so, again, this is m total times 3 meters per second squared. So now this is Fg plus m total times 3 meters per second squared. Now this is m total right here, right? I can actually factor this out. Let's write m total times 9.8 meters per second squared plus 3 meters per second squared. Because this is mg, right? M total times g. So I factor out m total and I get this. So now all these answers are the same, except that instead of 9.8, it's all 12.8. Right? So that's part B. Part C, now it has a negative acceleration. Right? So it's accelerating downward. What I'm going to do here then is make this negative. Negative, negative. So this then just becomes negative minus 3 meters per second squared. And that's what I'm expecting, right? If it's accelerating downward, I'm expecting the tension to be less than the force of gravity on that. So the force of gravity is winning and it's accelerating downward. So this now ends up being 6.8 meters per second squared. Okay. Good. So now we've got 2 more examples. Let's take a look. All right. Imagine now in this situation, this force is 10 newtons. And so what I'm going to do first is kind of break this up. So for this one, I have this tension, right? That's the free body. There's also the normal force and the gravitational force, but we're going to ignore that for now. There's no friction. For this 1 kilogram, there's 10 Newton force up, and then I also have the tension pulling down, so it's the same as this. And then I'm also going to have this, which is going to be Fg sine of theta. That's the parallel force pulling down. Okay. And so they all have the same acceleration. Because this object only has one force on it, the net force is equal to ma. So that's the tension is equal to 3 kilograms times the acceleration. So now when I write the equation for this, the net force equals the mass times the acceleration. The net force is this, so the 10 newtons, minus the tension, minus Fg sine of theta. And if Fg is 10, let's use 10 for this. 10 is 10 meters per second squared as the value for g. And quick thing, notice if this is 10, the angle is 37 degrees. That means this is 37 degrees. 37 degrees, you should program this into your head. That's the angle of a 3-4-5 right triangle. That's the small angle in a 3-4-5 right triangle. So this is 10, this is 8, this is 6. You save yourself some calculator punching that way. Just remember, 37 degrees is the angle in a 3-4-5 right triangle. Trying to make it easy on you. And so then this would be 10 sine of 37 degrees, but it'd actually be 6, right? So 6 equals m, which is 1, times a. But t is also this thing, right, 3a. So I can do 10 minus 6 was 4. So 4 minus 3a equals a. So 4 equals 4a. So the acceleration is 1 meter per second squared. Here's the other way to do this, all right, the way that I like a little bit better. It's something of a shortcut. What we did here was we used these bodies individually as separate systems and then found the thing that they had in common and substituted. That happens automatically if we take both of these as the system and I just ignore internal forces. What's the internal force between these two things? The tension. So sigma F equals ma. What are all of the external forces? Well, I've got the 10 newtons this way, right, pulling up along the ramp here. And then what are the external forces pulling against it? Well, just this, right? This Fg sine theta. So that would be 6 newtons equals, and then m, what's the total mass involved? The total mass is 4 kilograms times the acceleration. So this is 4 newtons equals 4 kilograms times the acceleration. So the acceleration, again, we get 1 meter per second squared. So you can see it works both ways. That way is shorter, it's simpler. But you need to understand how systems work and be able to analyze what are the internal, what are the external forces. So let's take a look at example 4. And now for this last example, this is a remake because I messed it up the first time. And here we go. What we have is this system with 2 blocks and a pulley in the middle. And we're going to do this the easy way, where the system is both blocks. Since the system is both of these blocks, we ignore the tension, because the tension is an internal force to the system of both blocks. When we write our Newton's second law equation here, then the only 2 forces I have are this, and I need to pick a direction. I need to guess at what the acceleration is going to be. So let's just guess that the acceleration is going to be that way. And so I'm going to make this my positive force. So this is Fg sine of 30, and I'll make this my negative force, Fg sine of 60 equals ma, and this mass is going to be the total mass of both blocks together. Now this block is 30 newtons, and this is 20 newtons, and they have a total mass of 5. So this ends up being 15 minus 17.3. So I end up with negative 2.3 is 5a. So the acceleration is negative 0.46 meters per second squared. All right, so that means that the acceleration is actually this way at 0.46 meters per second squared. And then to find the tension, what I can do is I can set up an equation for one of these guys. Let's say this one. And here is Fg sine 60. It's accelerating this way at 0.46 meters per second squared. And this is the tension. And so Fg sine of 60, which I know is 17.3, minus the tension equals the mass times the acceleration. And so the tension is going to be Fg sine of 60 minus ma. Right, solve that. So this is 17.3 minus 2 times negative 0.46, which I don't have. But if you do that, minus 2 times 0.46, you should get 16.4 newtons, about. So that's what the tension is in the cord, and the tension is going to be the same in both places. Okay, and that's it.